Let us continue our discussion on matrices. Now we're going to basically talk about the inverse of a matrix. We discussed matrices. Now we want to find the inverse of a matrix if possible. Let's begin by a very easy definition. Definition of inverse of a matrix. Suppose you have an n by n matrix. Let A be a square matrix of order n. We say that matrix A is invertible or non-singular when we can find an n by n matrix like B such that if we multiply A and B, the result is identity matrix of the same size, and also BA is equal to the identity matrix of the same size. As you remember, IN is the identity matrix of order n. In this case, the matrix B is the multiplicative inverse of matrix A. We say that matrix B is the multiplicative inverse of matrix A. If matrix A doesn't have an inverse, we say that it is singular or non-invertible. If matrix A has no inverse, we say that matrix A is singular or non-invertible. So let us familiarize ourselves with these terminologies. We're going to use them back and forth in different linear algebra books. You might see different terminology. We have a nice theorem that we're going to write a short proof for it. If A is an invertible matrix, if matrix A is an invertible or non-singular matrix, then its inverse is going to be a unique matrix. Then its inverse is a unique matrix, and it is represented by, we're going to write down matrix A, and it has -1 on its exponent. But this is called just the inverse of matrix A. So let's begin. It's just a short proof for you. So if someone asks you, hey, prove the uniqueness of the inverse of a matrix, you can write it this way. If A is an n by n invertible matrix, then it has an inverse like matrix B. Matrix B. So this is by definition, right? This is by definition. And the property is if you multiply A and B, it's equal to identity matrix, and it's the same as the multiplication between B and A. So now suppose matrix A has another inverse, right? So suppose matrix A has another inverse like matrix C. So by definition again, we have AC equals to identity matrix, which is equal to CA. Well, okay, take a look at this guy here. I have AB, right? I know A times B is equal to identity matrix by definition that B is the inverse of A. Well, if I multiply both sides by matrix C, let us multiply both sides by matrix C. Why not? You're allowed to do that. So I'm going to multiply left-hand side by matrix C. So you get C, A, B, which is C times I. Now, if I group these two together, C and A, see what happens. I have C times A multiplied by B, and on the right-hand side, Ci is nothing but matrix C. But pay attention here. I have C times A. C times A is equal to identity matrix. So this guy is I. So I have I times B, and on the right-hand side, I have matrix C. Basically, I times B is equal to B, and on the other side, I have C. So what's the meaning of that? It means that B and C are equal to each other, or basically, they are the same matrix. So we just proved the uniqueness of inverse of a matrix. So if a matrix has an inverse, that inverse is unique. So let us begin finding the inverse of a matrix. How do we find the inverse? We're going to start by finding the inverse of a 2 by 2 matrix first. Let us find the inverse of some matrices. Example. Let A be matrix 1, 4, -1, -3. Our goal is to find the inverse of this matrix. Basically, we are looking for to find the inverse of A. We are looking for another matrix like B that has A, B, C, D as its component. So the entries of B are not given. Our goal is to find them. And the fact that If I multiply A and B, it's equal to identity matrix. So on the other side, let me use a different color for identity matrix of order 2. Just pure multiplication. It's not that complicated. So matrix A, let me grab this guy, copy and paste it here. This is matrix A. Let's multiply by matrix B, which is AB, CD, and on the other side, we have identity matrix that you already know the entries of. So take a few minutes and find the entry A, entry B, entry C, and entry D. It's just pure multiplication, and finding the rest of them are algebra. Then add your answers in the chat, everyone. It's a good practice, just pure multiplication. Once you're done, please write your answers in the chat. You're finding the values for A, B, C, and D. By multiplication, you're basically finding the dot product between these two vectors. So here you have 1 times A, so you get A plus 4C. And the second entry of this new matrix, I'm going to do the multiplication here, find the dot product, 1B plus 4D. And let us move on to the second row. Here we have the dot product between -1 and A, which is minus A, minus 3C. And finally, we have the last one. Use this color for this. You get negative B minus 3 D. And on the right-hand side, we basically have our identity matrix. Just set up the algebra. It should be super easy for you. The entries must be equal entry-wise. And then just do the algebra. Perfect. So here we go. Let us set this up. You have A plus 4C equals to 1. Then you have negative A minus 3C equals to 0. You also have B plus 4D equal to 0. Negative B minus 3D is equal to 1. So you have two equations in two variables that you can easily solve. Here C is equal to 1. So if you plug in, for example, in the first equation, A is 1 minus 4, which is negative 3. Okay, with the same argument, if you add these two, D becomes 1. And if you plug that back into the, for example, first equation, B becomes negative 4. So this is the inverse of the matrix. Is equal to negative 3, negative 4, 1, and 1. We have a trick as well, right? Let me write down the trick for you here to show you we get the exact same result. If you have a 2 by 2 matrix, you can apply a nice trick, shortcut. If A is a 2 by 2 matrix with entry A, B, C, D, then if AD minus BC is non-zero, the inverse of matrix A is as follows. So you have 1 divided by AD minus BC multiplied by, you're going to switch the entries on the main diagonal. So now you get DA, and you're going to multiply the entries that are not on the main diagonal by negative sign, negative B and negative C. So let us check this matrix and using this trick, right? This is my matrix A. I went over a lot of algebra. So this is matrix A. So let me calculate AD minus BC. AD minus BC is equal to, I have negative 3 minus minus 4 or plus 4, which is 1. So this is non-zero. It means that I can apply this nice trick and find the inverse of this matrix. The inverse of this matrix is 1 divided by 1 scalar multiplication with, now I'm going to switch the entries on the main diagonal, negative 3 and 1, and I'm going to multiply the entries that are not on the main diagonal by negative sign. And this guy is basically negative 3, negative 4, 1, and 1. So as easy as that, you can find the inverse of the matrix here. So from the result, using algebra to applying this nice trick. But the thing is that if you have, for example, a matrix with larger sizes, this trick doesn't work. We need to apply other methods. In this method, we're going to basically write down the adjoining matrix. So in general, to find the inverse of a matrix, we need to write the adjoining matrix, matrix A. So let me move this here so I can add that I'm talking about matrix A. And I'm going to find the adjoining matrix by identity matrix with the same size. Then we're going to apply elementary row operations. Then apply elementary row operations and then convert this matrix into the matrix that you're going to see identity matrix on the left-hand side, and the matrix on the right-hand side is going to be the inverse of your matrix. So the entries on the left-hand side now are identity matrix, and the entries on the right-hand side are going to be the inverse matrix. Let me show you one example so you feel more comfortable about this method. Okay, example. Find the inverse of the following matrix. So here I'm going to give you matrix A that has the following entries: 1, negative 1, 0, 1, 0, negative 1. Then you have negative 6, 2, and 3. So this is a 3 by 3 matrix, am I right? A matrix of order 3. Let us form the adjoining matrix, which is going to be A adjoined by identity matrix of the same size. All right, so let us just grab this matrix. I don't want to rewrite this. And then here, let me move this guy over here and add. I'm going to use a different color for identity matrix 1, 0, 0, 0, 1, 0, 0, 0, and 1. Let me move this guy a little bit further down. So remember that your goal is to convert the matrix on the left-hand side to become the identity matrix. All right, this is our goal. This is what we're trying to do. Well, I don't have any issue with the very first entry. All right, the very first entry is basically 1. Okay, let me erase this. So we can apply this method here. So the very first entry is 1. We don't have any issue with 1. Let's call it R1, R2, and R3. The entry below 1 needs to be 0. Also, this -6 needs to be 0. So what we can do, we can basically multiply the very first row by -1 and add it to the second row. Also, multiply the first row by 6 and add it to the last row. So let's see what's happening here. I have 1, -1, 0, and enter is for identity matrix. And let me close this up. This is just the row operation. Am I right? If I multiply the first row by -1 and add it to the second row, my whole second row will be changed. So here we go. I get 1 minus 1. I have 0 plus 1. And I have -1 plus 0. Then I have 0 plus -1. And then I have 1 minus 0 or plus 0. And then you have 0 minus 0. I'm going to do the same thing to the last row as well at the same time to save time. So I have -6 plus 6. I have 2 minus 6. I have 3 minus 0. And then I have 0 minus 6, then 0 minus 0, and 1 minus 0. So let's see what's happening here. This becomes 1, 0, 0, -1, 1, -4. I have 0, -1, and 3. Then I have 1, -1, -6, 0, 1, 0, 0, 0, 1. Let's take a look at this, make sure we haven't made any algebra mistake. Everything is going as planned. Okay, I multiply this by 6, so it should be just +6. Am I right? Yes. Let me fix this one. Beautiful. Awesome. And okay, here we have just plus. Okay, cool. So far, we're good with the very first column. The second column, it has 1, but the entries above and below must be equal to 0. So we're going to do the same thing here. You can relabel these as R1, R2, R3 again. These are your new rows, but again, multiply the second row by 1 and add it to the first row, or basically add R1 and R2 together, and then multiply the second row by 4, 4 times R2, and add it to the third row. Let's see what's happening here. What do we have? So I'm going to write down the entries for the second row, 0, 1, -1, and then here you have -1, 1, and 0. Okay, let's close this up. Perfect. So if I add these two together, I have 1 plus 0, -1 plus 1, 0 minus 1. Then I have 1 minus 1, 0 plus 1, and 0 plus 0. And down here, I have 0 doesn't change at all. So I have 4 minus 4. I have 3 minus 4. And then I have 6 minus 4. I have 4 plus 0, and then 0 plus 1. Oh, let me change the color here. Okay, 6 minus 4, and 0 plus 4, and 1 plus 0. Perfect. So we can simplify this. As you can see, it takes time to do the computation. Sometimes you might make mistakes. So be careful, always go back and take a look at what you did. The algebra is correct. And 0. And here we have 0, 1, negative 1, 0, 0, and negative 1. And then you have 2, 4, 1, negative 1, 1, and 0. Okay, almost done. Now I need to multiply the third row. Let us call this again R1, R2, R3. This is the issue. And then if I multiply the third row by negative 1, negative 1 times R3, this guy becomes, so I'm going to just grab this, copy and paste it down here to save a little bit of time. This becomes positive 1. So here you have a positive 1, and then you have negative 2, negative 4, and negative 1. Now you just need to add the third row to the second and first row, and then you're done. So add R3 to R2 and add R3 to R1. Then we have our identity matrix. Okay, perfect. Now let me copy this guy down here. If we do the addition, this guy becomes 0. And then this guy becomes 0 as well. And we're going to apply the same thing to the green entries as well. Here, if you add R2 and R3, this becomes negative 3. So negative 3, and then becomes negative 3 again. And here I end up with negative 1. And I end up with a negative 2. And then negative 3 again. And negative 1. Negative 3. And negative 1. So it seems like my inverse is this matrix here. This matrix is the inverse of your original matrix. We can test that as well, right? So inverse of A is negative 2, negative 3, negative 1, negative 3, negative 3, negative 1, negative 2, negative 4, and negative 1. We can also check our process to make sure we are on the right path. You can basically multiply matrix A by its inverse, supposedly inverse, and make sure it is equal to identity matrix. Make sure to check that to make sure you have a correct inverse matrix. So what are the properties of inverse of a matrix? Important properties for inverse. Of inverse of a matrix. We have nice theorems about the properties of inverse of a matrix that we're going to write some of them here. Theorem. So suppose you have an invertible matrix. Let A be an invertible or non-singular matrix. Let K be a positive number. We're going to introduce another non-zero number, and let us just call it, for example, C. Let small c be a non-zero number. So these are the pieces of information that we are having so far. The very first property is the inverse of the inverse of a matrix is equal to that matrix. This is the very first property. But how do we prove this property? Let's begin. If I ask you to prove something, you can basically use the definition and use the direct proof. By definition, we can prove this property. What does it tell us? This property say that the inverse of the matrix A is A itself. So remember that you can call this guy, for example, matrix B, all right? So you're going to say that, hey, if I multiply A by its inverse, it must be equal to identity matrix. Okay, this shouldn't be that difficult, since the product of A and the inverse of A by definition is identity matrix. So A multiplied by its inverse is equal to identity matrix, all right? So what's the meaning of that? It means that this matrix, matrix B, is the inverse of matrix A. This is your matrix B. So B, which is just, representative of the inverse, is the inverse of A. But remember that when you have the inverse, you can write it this way. You can say that, hey, A is equal to the inverse of its inverse. As simple as that. Let's take a look at the second property. The second property says, what if you raise a matrix to a power? It means that you multiply a matrix by itself multiple times. Like if I take matrix A and raise it to some exponent. What if I take the inverse of the matrix A multiplied by itself k times? This is basically writing the multiplication of the inverse of A k times by itself, which can be written as, hey, I have the inverse of matrix A, and now I'm raising it to power k. So again, if you have matrix A and raise it to power k, and then taking the inverse, is the same as finding the inverse of that matrix and raising it to power k. We can prove this property using induction. This is one of the methods that we can use. So you can prove by induction. So if you have time, take a look at the proof. The proof is very easy to conclude using induction. Let's take a look at another property. So what if I multiply a matrix by a number like C and find the inverse? In that case, it is equal to, you need to write down the reciprocal of that number and multiply it by the inverse of matrix A. Remember that C is non-zero number. What is the sketch of the proof? Basically, we are finding the inverse of C times A, and we're saying that, hey, the inverse of CA is 1 over C times the inverse of A. So we want to show that the inverse of CA, let me make sure this is capital, is 1 over C times the inverse of A. But by definition, if you have inverse for a matrix, if you do the multiplication, then you can basically show that it's equal to identity matrix. By definition, we need to show that their product is identity matrix. So let's begin. If I multiply CA by this potential inverse, 1 over C times the inverse of A, remember the properties of scalar multiplication. You can basically group these together. C multiplied 1 over C, and A is multiplied by its inverse. But C and C, they get canceled out, and this guy is nothing but identity matrix. So we just showed that you have 1 times identity matrix, or basically you have the identity matrix. So we just showed that the product of CA and 1 over C multiplied by inverse of A is nothing but identity matrix. So we can conclude that the inverse of CA is equal to 1 over C times the inverse of A. And the last property that we're going to discuss is about the transpose. If I have the transpose of a matrix and I want to find its inverse, I can find the inverse of the matrix and then find its transpose. One of your friends asked, what is induction? So in short, induction is a method of proof. Induction, review. Induction or mathematical induction is a method of proving special cases of mathematical statements. So suppose you have a general statement. Let P of n be a general statement. Like what? In our case here, we can say that, well, a to power n, let me use a different color, a to power n inverse is equal to a inverse to power n. So to prove this statement, you're going to start by a very basic case. We're going to call it inductive step or inductive base. In the base case, you're going to prove this equality or a simple case like n equals to 1. So you're going to prove P of 1 is true. So in this case, you're going to say that, hey, a to power 1 inverse is the same as inverse of the matrix raised to power 1. But is this true? Yes, of course. When you have power 1, it's the same as your matrix itself, right? Here you have the inverse of the matrix. On the other side, you also have the inverse of the matrix. Left-hand side and right-hand side are equal to each other. So this is your very base case. Then you move on to inductive hypothesis. Inductive hypothesis says, assume pk is true for any k less than equals to n. Now, prove this statement for pk plus 1. So what's the meaning of that? We assume that. We hypothesize that. If I have a to power k and find the inverse, it is equal to the inverse of the matrix to power k. Now we need to show that it's true for the next step. What's the meaning of that? It means that we need to show that a to power k plus 1 inverse is the same as inverse of the matrix to power k plus 1. But this should be easy for you because you can break this guy down into a smaller portion. For example, this one can be written as a to power k times a, and finding the inverse. And on the right hand side, you have the inverse of the matrix to power k times a inverse to power 1. Left hand side and right hand side are easy to calculate. Remember that when we are talking about the inverse of the matrix, if you have AB and you're finding the inverse, it's switched. So it is the inverse of A multiplied by A to power K inverse. But we know that from the inductive hypothesis, we have this property. Can use the property here and then rewrite this guy as the inverse of A multiplied by inverse to power K. This can be written as just basic multiplication. AB is the same as BA, so you can switch these two. This is the inverse of A to power K multiplied by the inverse of matrix A, which is basically the same as what we have on the right-hand side. So left-hand side and right-hand side are equal to each other. So left-hand side is equal to right-hand side. So by induction, we just proved that this statement is true. Okay, now let me show you how to show that the inverse of AB is equal to inverse of B times inverse of A. We have a nice theorem here. So in this theorem, let A and B be two invertible or non-singular matrices of order n. Then we can conclude that their product AB and also BA are invertible and the inverse of AB is the inverse of B times the inverse of A. The proof is very easy. So to prove this statement, we want to show that the inverse of B times the inverse of A is actually the inverse of matrix A times B. But how are we going to do that? We need to multiply these together and show that the product is equal to identity matrix. To do that, we need to multiply AB and B inverse times A inverse and show that this product is actually identity matrix. So let's begin. AB is multiplied by the inverse of B by inverse of A. We can group these together differently. I can take these two and group them in the middle. So what's happening? I have A times B times its inverse multiplied by inverse of A. But again, since we are multiplying B by its inverse, it is equal to identity matrix. So you get A times I times the inverse of A. But remember that when you're multiplying by identity matrix, it is basically the matrix itself. You have A times inverse of A, which is again identity matrix. So we just showed that B inverse A inverse is the inverse of AB. So what's the meaning of that? It means that if I find the inverse of AB, it is B inverse multiplied by A inverse. You can generalize the idea as well, right? Quick note for you. So if I have more product, more multiplication, we can generalize the idea. If I have some matrices, A sub 1, A sub 2, A sub 3, A sub 4, AN minus 1, AN, these are invertible matrices. They are multiplied together. I want to find the inverse of their multiplication. This is equal to the inverse of AN multiplied by the inverse of AN minus 1 multiplied by the inverse of AN minus 2 dot 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 the inverse of A3, the inverse of A2, and the inverse of A1. And again, please note that all of these matrices, A sub i's, are invertible. I ranges from 1 to n. We have some nice cancellation methods. In general, cancellation method is not true. We can apply cancellation method if we have invertible matrices. So it's a good lemma for you. Let us write down this lemma. Cancellation properties. If C is an invertible matrix, if matrix C is invertible, or as we mentioned, non-singular, it means that it has an inverse for any matrices A and B, we have the following. If you have A times C equals to B times C, you can basically multiply both sides by the inverse of C and get rid of C. We conclude that A is equal to B. A quick proof. AC is equal to BC and C is invertible. So the inverse of C exists. Multiply both sides. Multiply both sides by the inverse of C. So here you get A times C multiplied by inverse of C. On the right-hand side, you have B times C multiplied by inverse of C. But as you know, the product of C with its inverse is identity matrix. So we can just show that you get AI equals to BI, or A is equal to B. You have the exact same thing if you switch this multiplication. If CA is equal to CB, then you can conclude that A is equal to B. So again, a quick proof is that now you multiply everything by inverse of C from left. So this is the case. Short proof. These are easy proof for you. CA is equal to CB, and C is an invertible matrix with inverse denoted by inverse C. So if we multiply both sides by inverse of C with the same argument, it's CA equals to CB. Again, you end up with the inverse of C multiplied by C, which is identity matrix. So A is equal to B. So this is the cancellation method that you can apply here. You need to have invertible matrix to do that. Remember that in previous exam, when we talked about cancellation, cancellation is not in general correct when it comes to matrix multiplication. You have to have an invertible matrix here. Now we can use this information for the system of equations and show that system of equations have unique solutions if your coefficient matrix is invertible. That's interesting. Take a look. Here. Consider the system of equation AX equals to B. If A, or the coefficient matrix, is invertible, then the system has a unique solution. That unique solution is X to be inverse of A multiplied by the column of constant values. The proof is very easy. Let's take a look at the sketch of the proof. Since the coefficient matrix or A is invertible, it has an inverse. Let us call it inverse of A. Now multiply the system AX equals to B by the inverse of A. So what do you get? You get inverse of A multiplied by AX equals to inverse of A multiplied by B, right? So as you can see, on the left-hand side, the inverse of A multiplied by A is nothing but identity matrix. So you get identity matrix times X equals to inverse of A multiplied by B. But IX is equal to X. So X is inverse of A multiplied by B. But remember that we said the inverse of a matrix is unique, all right? So you have a unique matrix on the right-hand side, and it's multiplied by B. B is also fixed, so you get a unique value. Note that since the inverse of A is unique, inverse of A multiplied by B is also a unique matrix. So the system has a unique solution. So we're done with the proof, all right? Let's take a look at a few examples here, everyone. Practice a little bit. So for this question, I want to find values for X such that the matrix is equal to its own inverse. Find value or values of X such that A is equal to its inverse. The very first matrix that I'm going to give you is a 2 by 2 matrix with entries 3x, -2, and -3. Work on this question. Write your answers in the chat. What are the X values? We're looking for X values such that matrix A is equal to its inverse. Remember that for a 2 by 2 matrix, you have a nice trick. If matrix A is 2 by 2, A, B, C, D, with the condition that later on we're going to talk about the determinant, AD minus BC is non-zero, then the inverse of the matrix is 1 over AD minus BC. You're going to switch the elements or entries on the main diagonal and then multiply the rest of the entries by negative sign. So we want to set these two matrices equal to each other, right? This is what we're trying to do. We have one answer in the chat. The rest of the class. What you got? Should be very easy to find X, right? So this is my A. My inverse is equal to 1 divided by AD, which is 3 times -3. minus BC minus negative 2 times x. And what I'm going to do, I'm going to switch these two, negative 3 and 3, and then multiply the entries that are not on the main diagonal by a negative sign. Very good. We have some answers. We have 4, we have 2, we have 6, we have negative 4. Somebody wrote down a matrix. Okay, thank you guys. So let's solve this together. This is equal to 1 over 9 plus 2x, right? Negative 9 plus 2x, and then here you have negative 3, negative x, 2 and 3. So if you do the scalar multiplication, you get negative 3 divided by 2x minus 9. Then you have negative x divided by 2x minus 9, 2 divided by 2x minus 9, and 3 divided by 2x minus 9. Now you're just going to set these. I circled the wrong one. Okay, let me see. Okay, here we go. We're going to set these two matrices equal to each other, right? Their entries must be equal, right? So for example, you can take 3 and set it equals to negative 3 divided by 2x minus 9. See what happens. Set 3 equals to negative 3 divided by 2x minus 9. But here you can cancel out 3 and 3. You end up with 2x minus 9 equals to negative 1. So 2x is equal to 9 minus 1, which is 8. So x is 4. It doesn't matter which entries you set equal to each other, right? For example, you might say, hey, I want to set these two entries equal to each other, like x and negative x divided by 2x minus 9. You get the exact same result. X or set x to be equal to negative x divided by 2x minus 9. Here you can simplify this. So you get 2x minus 9 equals to negative 1. 2x becomes 8 and x becomes 4 again. So the answer that you're looking for is 4. Very good. Let us take a look at another one. Let me give you trigonometric matrix. Find the inverse of the following matrix. Another example. Inverse of matrix is given to you as, here you have sine of alpha, cosine of alpha, negative cosine alpha, and sine alpha. So what is the inverse of this matrix? If you find the inverse of this matrix, what is the very first entry? All right. Just write down the first entry for me. Very good, thank you. So take a look. So the inverse of this matrix is equal to 1 divided by sine alpha multiplied by sine alpha minus cosine alpha times negative cosine alpha. What are you going to do? You're going to switch sine with sine, stays the same, and multiply the entries that are not on the main diagonal by negative sign. Very good. We're going back to trig identity. You get sine squared alpha plus cosine squared alpha, and you're multiplying that, finding the scalar multiplication between this scalar and your matrix here. But remember that trig identity say this is 1. So the inverse of matrix is equal to sine alpha, negative cosine alpha, and sine alpha. Let's take a look at another cool statement. Example for you. If A squared is equal to A, if you multiply matrix A by itself and it becomes A, then identity matrix minus 2A inverse is the same as itself. So how do we prove this? What is the very first step in proving this statement? Remember that our goal proof. Our goal is to show that the inverse of I minus 2A is I minus 2A. So it means that if I multiply these together, the outcome must be equals to identity matrix. By definition, if I multiply I minus 2A by I minus 2A, it must be equal to identity matrix. It must be identity matrix. So let us begin. Let us multiply I minus 2A by I minus 2A. So basically, we are using simple distribution, right? So distribute I into parentheses, then distribute negative 2A into parentheses. What do we get? We get I times I minus I times 2A minus 2A times I plus 4A times A. So these dots are basically showing multiplication between matrices. It doesn't mean that we have a dot product. Take a look. So here you have multiplication between identity matrix and itself is identity matrix minus. So here, if you switch these around, you have 2IA minus 2AI plus 4A squared. IA and AI, they are the same thing. So this becomes I minus 2A minus 2A plus 4A squared. So you get I minus 4A plus 4A squared. Now take a look. We have a nice property. If you take matrix A and raise it to the second power, you get your matrix A back. So you can use it here. Wherever you see A squared, this is the same as matrix A. So here you have I minus 4A plus 4A, but these two are opposite of each other, so you end up with I. So what's the meaning of that? We just showed that I minus 2A multiplied by I minus 2A is equal to identity matrix. So by definition of the inverse of a matrix, the inverse of I minus 2A is equal to I minus 2A. So these are nice proofs, nice property that you can use and prove different statements. Let us go over another one together. There are many statements that you can prove when it comes to properties of matrices, especially when it comes to the inverse. Just a quick note for you. We say that a matrix is idempotent if you multiply matrix A by itself, it results in matrix A. So if you see the word idempotent matrix, it means that it has this property. If you multiply matrix A by itself, you get matrix A back. Sometimes they specify idempotent matrix in textbook. Some other times they just skip it. Let's take a look at another example. In this example, we want to prove that if you have three matrices like A, B, and C, if we have square matrices like A, B, and C, and if you multiply these together, the product is equal to identity matrix, then B is invertible, then matrix B is invertible, and the inverse of B is equal to C times A. Let me move this a little bit here. So what's the sketch of the proof here? Let's take a look at the short proof. Since the product of ABC is equal to identity matrix, if we multiply both sides by the inverse of matrix A, assuming that A is invertible, assuming that A is invertible, multiply both sides by inverse of A. So you get inverse of A times ABC equals to inverse of A multiplied by identity matrix. So basically here you can get rid of the inverse of A multiplied by A, assuming that A is invertible, it is going to be identity matrix. So you get I times BC is equal to inverse of A. Now, assuming that C is also invertible, assuming that C is invertible, we're going to do the same thing. We're going to have to multiply both sides by the inverse of C. So take a look with the same argument. Assuming C is invertible, you get B times identity matrix, and on the other side you have the inverse of A multiplied by inverse of C. So B becomes inverse of A times inverse of C. So basically, what do we see? We see that B is equal to CA inverse. No, we need to assume that A and C are invertible. If they are not invertible, well, finding the inverse of B is also pointless. Good question. So basically, the inverse of B is equal to C times A. Let's take a look at another cool statement. As I mentioned before, we have a lot of statements when it comes to inverse of matrices. In the following statement, we have if A is an idempotent matrix, then either A is singular or A is equal to identity matrix. Then this is a bold statement, am I right? Then A is singular or A is nothing but the identity matrix. Okay, let's begin. Proof. Since A is an idempotent matrix, it means that if you multiply A by itself, it is equal to A. Now, if A is invertible, the inverse of A exists, right? So if the inverse of A exists, and we know that A is idempotent matrix, multiply both sides by the inverse of A. See what happens here. Take a look. I have inverse of A multiplied by A times A, which is A times A. And on the other side, I get the identity matrix. So assuming that A is invertible, the inverse exists. Now what happens here? I have the inverse of A multiplied by A, which is again identity matrix. So I have identity matrix times A equals to identity matrix. So on the left-hand side, I have A. On the right-hand side, I have identity matrix. So again, if you have an idempotent matrix, it's either singular. If it's not singular, it must be equals to identity matrix.